Hello. Today's problem is dealing with some more of curve sketching. This time we're going to work with the first derivative and the second derivative. So recall what we learned at stationary points. That refers to places where the function has zero velocity. So that would be horizontal tangent lines. In other words, I always talk about stationary points as flat, if you will. Inflection is the point in which a function changes concavity. So there's we're going from concave down to concave up, or vice versa. So both of these conditions have to be true for this general polynomial where a, b, and c are parameters that are unknown. The book asked us to show that b is equal to 8a squared, but after we reviewed this, we discovered that it's actually b is equal to negative 1/3 a squared. Pretty significant. I put this into Desmos to check, and it turns out this is in fact wrong, and this does in fact work, and so I'll demonstrate that as we go. Suffice it to say, however, that even if this or this is true, the way that you do this problem, the setup, is going to be the same no matter what. So the clues that we get are the fact that the stationary points, which means the first derivative has to equal 0, and inflection points, which means the second derivative has to equal 0. So I take the first derivative, and in order for the first derivative to equal 0, my first derivative has to equal 0. This I see as a quadratic equation. Since I don't know a or b, I can't factor it, so I have the only solution method I know, the old quadratic formula. And I've worked to simplify the quadratic formula a little bit, and one of the things I noticed, this might be a little tricky for some, but I did a couple steps in my head. I factored out a 4, because 4 and 12, you factor out that 4, and then I took the square root of it, factored out to be a 2 in front here. So then I divided 2, divided 2, divided 2, so that everything is just a little cleaner, a little nicer. It's not a mandatory step, but it is kind of nice. Then I take the second derivative. I need that to be equal to 0 as well. So when the second derivative equals 0, much easier to solve. X has to be 1/3 of a. So what we're learning here is that both of these conditions must be true in order for the statement in the beginning to be true. That is to say, the x must be this combination of a's and b's, but x has to simultaneously be equal to 1/3 of the value of a. So whatever a is, we take a third of that, and that's going to be our x value. If both of those conditions are simultaneously applied, then the stationary point will be an inflection point. This equation then just needs to be solved. Notice that there's a and b in it, so there are infinite possibilities here, but we'll have a in terms of b once I solve this. So first I triple both sides, then subtract a from both sides, square both sides, and sure enough, b is equal to negative 1/3 a squared, which is the thing we were supposed to prove over here. Here's where it gets fun. We programmed Desmos where this represents the polynomial that was given to us, and I made the c variable changeable, which means we can move the graph up or down. That's all that does, is just change that. And then I changed the a value to be something that can change as well, but the b value has been tied or linked to the a value by this. So I'm not going to change b using a slider. I'm going to change b by whatever a is. The b is going to be the square of a times negative 1/3. If that condition is in place, then we notice in our function that there's only one stationary point, and it's a stationary inflection. No matter which value I choose for a, I'm always going to have the same conditions apply. So that's the way that we can verify that the book was definitely wrong, and of course I'm definitely right. So thanks for watching.